Who would win, a trillion lions or the sun? It is the age-old question that has captivated humanity for millennia, and often one of the questions I get asked at the end of a lesson when I ask the class, do you have any random physics questions you've always wanted to know but never had the opportunity to? The easy answer is the sun, but that doesn't fill a whole video, or cut off follow-up questions like, what if they attacked at night? So let's look at the issues properly to settle this once and for all. No. What do you mean I can't just reuse this gag from 2 weeks ago? According to the International Union for Conservation of Nature, or IUCN for short, the population of wild lions in Africa was estimated to be between 22 and 25,000 in 2018, with less than 700 to add to that from India. This is massively down from their population even in the last 100 years, with global conservation painting an even bleaker picture. There are a number of reasons for this drastic drop, from loss of habitat to increased conflict with humans to poaching, to name just 3. So, ignoring the ethics of hurling a whole bunch of lions at a main sequence star, there simply isn't the population currently to get anywhere near to the 1 trillion lions that are often asked for. This is just 0.00002% of the required lions. Even if we looked at the number of lions that have existed through history, we still wouldn't get close to 1 trillion. As an aside, I decided to look at just how much land 1 trillion lions would need to happily roam on. The number of lions per square kilometre varies massively for where they live on Earth, with one of the highest densities in the Masai Mara National Reserve, having around 17 lions per 100 square kilometres. That's just under 6 square kilometres per lion. Scaling this up for our supposed 1 trillion lions, and they would need an area of 5.88 times 10 to the 12 kilometres squared to roam. The surface area of Jupiter is only 6.1 times 10 to the 10 kilometres squared, so around 1% of their required space, even if the lions somehow figured out how to float in the atmosphere of this gas giant. And as we've already looked at during our episode about skydiving on Jupiter, it might not be the best planet to live on. This is one part of the question that is open to interpretation. The sun is not a living thing, and I suppose the thing that keeps it going is the nuclear fusion at its core. So by defeating the sun, we would have to stop that nuclear fusion. There are 2 potential ways to do this that spring to mind. One is to rip a hole in the centre of the sun by firing something through it. The core itself contains 34% of the sun's total mass, so this would be no easy task. The other is to stop the fusion in the core by cooling it so much that the fusion can no longer take place. For this, we need to understand that the sun's core is currently at a temperature of around 15 million degrees C, and we'd need to cool it down to 10 million degrees C to stop that fusion. But before we consider how we could do this, it is important that we look at To say that the sun has a lot of stored thermal energy would be a massive understatement. A giant ball of plasma with a mass of 1.99 times 10 to the 30 kilograms and a diameter of around 1.4 million kilometers. That's over 300,000 times the mass of the Earth, with a diameter 200 times larger. Now, not all of the sun is going to be at the same temperature as the core, with different layers of its interior and atmosphere at a huge range of temperatures. Within the sun, the temperature generally drops more the further you go away from the core, with the surface temperature down to just 5,500 degrees C. This might make you think that you could heat-proof the lions to get them through the outer layers of the sun, but this does not consider the temperature of the atmosphere. The corona, usually visible during solar eclipses, has temperatures of up to 2 million degrees C. This is slightly hotter than the temperature that lions are generally used to and would be counterproductive for their living. For this section, let's assume we have a trillion adult lions. Males are heavier at around 190 kilograms, so let's use them for this hypothetical. A trillion of them would have a total mass of 190 trillion kilograms, or 1.9 times 10 to the 14 kilos. This might sound massive, and it is, but it works out as smaller than the asteroid that wiped out the dinosaurs, which is estimated to be in the 10 to the 15 to 10 to the 17 kilogram range. So, if our lions aren't even as heavy as that asteroid, what chance would they have against the sun? Not much. Even with this combined mass, our lions would burn up in the sun's atmosphere before they even got to the surface of the sun. If you wanted to reduce the time that the lions are being char-grilled and send them quicker into the sun, this would increase the resistive forces against them, generating more heat. It simply wouldn't work. If we're going to go hypothetical, having more lions than have ever existed, then we might as well throw in a teleporter in there as well. If we did this, we could consider whether the lions being added to the sun's core would cool it down enough to stop fusion from hydrogen to helium. To make the maths simpler, I'm going to make two big assumptions. One, wildly inaccurate, but helps make the maths a heck of a lot easier, and the other is okay, but not an exact number. The wildly inaccurate one first. Let's ignore the rest of the sun. That way, we can equate the heat energy lost by the core to the heat gained by the lions and not have heat flowing in from the rest of the star, which would have helped keep the core temperature up. The okay one is the composition of the sun's core. This varies depending on how deep you go, with the outer reaches around 70% hydrogen to 30% helium, whereas the center goes down to 34% hydrogen. Let's call it 50-50 on average, because again, it will make the maths easier. Two more assumptions. One, the lions have the same specific heat capacity as beef steak, and two, we can use the specific heat capacity for hydrogen and helium in their gas states, because that makes things easier. From here, the maths does get tricky, so if you've not looked at specific heat capacity before, brace yourself. The energy required to change something's temperature depends on its mass, the specific heat capacity, a value unique for each substance, and how much we want to change the temperature by. For this, we want to look at what the final temperature would be if the heat gained by the lions was equal to the heat lost by the sun's core, which we've split 50-50 into hydrogen and helium. The initial equation might look messy. We've used subscript L for terms referring to lions, capital H for hydrogen, and HE for helium. I have also used TF to indicate the final temperature and put in the values for the initial temperatures of the lion, hydrogen, and helium. From here, we can multiply out the brackets, then rearrange the equation so that all the terms with a TF on it are on one side, and those without are all on the other. And then if we rearrange to solve for the final temperature, it isn't enough to noticeably change the temperature of the core of the sun, not even by 1 degree C. It would be similar to boiling a kettle, pouring it into the middle of the Pacific Ocean, and expecting it to noticeably change the temperature of the oceans. Because of the significantly lower mass of the lions versus the mass of the core of the sun, and the lower specific heat capacity of the lions, the only way to noticeably change the core temperature of the sun is if the mass of the lions becomes comparable or even greater than the mass of the core of the sun. If my calculations are correct, to drop the sun's core temperature to 10 million degrees C, you would need 1.03 times 10 to the 30 kilograms of lion. That is 5.42 times 10 to the 27 lions, otherwise known as 5.42 octillion lions, or alternatively known as too many lions. No, not doing this anymore. No lions, no sun, no. This isn't what I signed up for. For more videos like this, please do like and subscribe, which will also help the channel to grow further. And if you do have questions about space that you would like answered, let us know in the comments. Until the next time though, please continue to watch this space. Thank you.